All right, welcome to The Explainer. Today, we're digging into a fascinating idea, one that claims physics missed a crucial question centuries ago. And this one single oversight might have caused a whole century of confusion about, well, the nature of our universe. So let's jump right in with a pretty simple but provocative question. When you think of a wave, what pops into your head? Ripples on a pond? Sound moving through the air? The source material we're exploring today argues that, for hundreds of years, physics has just assumed all waves are basically the same. But what if they're not? According to this theory, that one little failure, not stopping to ask, hey, what kind of wave is this, is what sent physics spinning down a rabbit hole. A rabbit hole that led directly to many of the paradoxes we see in quantum mechanics today. You see, from the very beginning, physicists looked at light and thought, that must work just like sound. And sound, is a wave that needs something to travel through, like air molecules. It's what we call a field wave. So the thinking went, light must also be a field wave, a disturbance moving through some kind of medium made of countless tiny particles. And that assumption? It just stuck. Nobody really questioned it. The author of our source material, Mathis, puts it this way. He's saying this isn't some minor detail. He frames it as a foundational error, one that's had massive consequences for how we understand reality. If it affects your calculations, it's not a subtlety, it's fundamental. So the default model was set in stone. A wave was a collective disturbance. The idea that one single particle could generate its own wave wasn't just considered wrong, it was pretty much unthinkable. Okay, so how did this one single assumption lead physics into such strange territory? Well, this is where we get into what everyone calls the weirdness of the quantum world. This timeline lays out the whole story. Back in the 1600s, the assumption is made. Then, fast forward to the early 1900s, an experiment starts showing something really weird. Single photons can act like waves. That just doesn't fit the field wave model. But by then, the source claims asking those basic mechanical questions had become off-limits. Verboten. So what happened? Well, instead of going back and re-examining that very first assumption, the author argues that physicists just created a whole new set of bizarre rules to explain the weird behavior. You've heard of them. Wave-particle duality, superposition. They became necessary workarounds for a problem that, this theory claims, shouldn't have even existed in the first place. All right, so now we get to the core idea of the source material. We're moving from the problem to the proposed solution, which introduces a simple but really powerful distinction. The proposed solution is surprisingly simple. What if the problem isn't the wave's behavior, but our very definition of the word wave? The argument is that physics has been lumping two totally different phenomena under the same name. And here's the big split. On one side, you have a field wave that's caused by lots of particles and the wave travels through a medium. Think of sound. On the other side, you have a spin wave, totally different. It's caused by a single particle and the wave travels with it. The analogy here is a spinning pulsar. One is a disturbance in a medium, the other is the particle itself moving and spinning. So just picture it. A single particle, like a photon, isn't just moving forward. It's also spinning. And as it moves and spins, it creates its own periodic wave pattern that travels right along with it. The key here is that the particle is its own wave generator. It doesn't need an external field at all. Okay, that's a neat idea, but does it actually solve anything? Well, let's see how the source applies this new framework to two of the biggest puzzles in physics, light and neutrinos. This brings us right back to the original problem, doesn't it? If a single photon can somehow interfere with itself in those classic experiments, how does this new model explain that? The answer, according to this theory, is that simple. The wave isn't some ghostly probability field floating around the photon. No, the wave characteristics we measure are a direct result of the photon's own physical spin. All that quantum weirdness just disappears, because the photon was never just a particle. It was always a particle with an inherent wave-like spin. Now, this framework then gets applied to another huge mystery, neutrinos. You know those ghostly things that can pass through planets without slowing down? The author proposes that neutrinos aren't really particles at all. They are the other kind of wave, a field wave. And this table here really illustrates the difference perfectly. A photon's identity is a real particle. Its wave type is a spin wave, and it loses its own energy when it hits something. Think of it like a tiny spinning pulsar. But a neutrino in this model is just a field disturbance, a field wave. It doesn't lose energy so much as it transmits it, kind of like a sound wave. And that distinction is absolutely key. And this difference in how they lose energy explains their behavior. When a real particle, a photon, hits something, it loses a bit of its own energy. But when a field wave, a neutrino, hits something, it's really just passing its energy pattern along to the next particle in the field. The energy moves on with almost no loss, which is why neutrinos seem to travel through solid matter pretty much completely unaffected. So, what's the big takeaway here? What does it all mean if we start to look at physics through this particular lens? The core argument is that decades of mind-bending quantum theory, duality, superposition, entanglement might not be descriptions of a fundamentally weird reality. Instead, they could just be really complex mathematical patches that were developed to fix a simple mechanical misunderstanding from the very beginning. The author presents this not as just some philosophical idea, but as a complete mechanical solution. By assigning the wave properties of light to the physical spin of the photon, he claims to have created a whole new system of wave mechanics that makes the old paradoxes simply vanish. And that's the provocative thought we'll leave you with. It's a powerful reminder to always question our most basic assumptions, because sometimes the key to solving the most complex mysteries might be found in the one question that nobody thought to ask. Thanks for joining us on The Explainer.